Okay, so in this particular video, we're going to start with the actual course outline that has been designed for a Calculus 1 course. So we'll be starting with the idea of informal limits. Before that, you guys need to know the syntax or the terminology that will be used in later parts of this course. Actually, for 99% of the entire course, this is the definition that we'll be using. So the limit as the value x approaches a particular value a for a specific function f of x has to be equal to L. Now what this basically means is you have a function f of x, which may be any function for that matter. Let's just define that function over here. So if fx equals 2x plus 4, which is basically just a straight line over here, it's nothing too difficult at this point. So basically at x equals 0, it's 4. So something along the lines of that. That's the line that we have, right? And the idea is that we have a limit approaching this particular function over here. So if I were to rewrite this as limit of 2x plus 4 as x approaches a particular value, let's call that 1 in this case, and I'll explain what this means later on. This has to be equal to a particular value. So the idea of a limit is that, and this is informal limits, that if we have the value of x that is inside the function shown over here approaching a particular value which is shown in the sign or in the syntax that's right below the limit written over here, then we can simply evaluate that by considering this graph over here, right? So this particular graph has values of x over here, right? So what we're trying to approach is the value of 1. In the concept of limits, whenever we're trying to get as close as we can to the particular function, in other words, what we're doing is we're getting closer and closer to that particular value of x. But at the same time, the idea is that we're getting closer and closer to the value of y as well that's mentioned over here. So what the limit is basically saying is we're getting closer and closer to 1 over here and closer to y on the y-axis, right? So eventually what's going to happen is we're simply going to have to plug in the value of the number we're trying to approach inside the actual function, and that gives us 2 times 1 plus 4, and that equals 6. So this basically means that as we get closer and closer to 1 over here at this particular point, then on the y-axis we're going to get closer and closer to this particular point. What you guys need to absolutely understand in trying to understand this new concept of limits is that there is a word known as arbitrarily. This is going to be used throughout this course, and the idea is that in a limit, whenever you're evaluating the limit, you may be plugging in the actual value in some cases, which we will discover in later videos what it symbolizes. But at this point in time, when you're plugging in values, it just symbolizes the fact that as you're getting closer and closer to 1 on the x-axis, as shown over here, you're getting closer and closer to the value 6 on the y-axis. So we have to keep this in mind, that this isn't exactly going to be 6, but is going to be arbitrarily close to 6. So this will be perhaps the most important concept that we're going to come across in this entire course, that it's never actually equal to that particular value. In both cases, in the x case as well and the y case as well. That is why we refer to this statement as limit of a particular function as x approaches 1. It's not x equal to 1, it's approaches. And at the same particular instance, we are referring to the value of 6. That's the value we're trying to approach on the y-axis. Now let's do a few more examples to illustrate this new concept that we've come across. So let's talk about a very different function. Let's talk about a quadratic function, which would be of this form maybe. And if you try to simplify this, this just turns out to be this function over here. So if we were to plot this function, which by the way is a skill you guys need to know for this course, if you are able to draw good graphs, then there is a very good chance that you'll be able to solve limit problems very effectively. So if I were to plot this function, I can see that if I plug in a -1 over here, it's going to have a value of 0 at this point. And if we were to plot if you were to plug in a value of 0, it would give me a value over here, right? So these two values give me a graph like that. So roughly that's going to be equal to the function that we're trying to plot, right? So if we try to find the limit of this function at a particular point, let's say it's approaching 4, what would that be equal to? So all we need to do in this case is apply the rule that we've studied in the earlier part of this video. Let's plug in a 4 instead of x. So we have the function x squared plus 2x plus 1 over here, right? So as x approaches 4 for this, all we need to do is plug in 4 squared plus 2 times 4 plus 1. It turns out to be 16 plus 8 plus 1, which is probably 25. So what we're trying to say at this point is that as we get close to the point 4, so if we try to label this turns out to be -1, that's 0, that's 1, that's 2, that's 3, and somewhere over here we have 4. So let's assume the graph is something like this at this point. So what it's saying is that if we have the value of x as close as to 4 as it can possibly be, then on the y-axis the value of the function basically that we're trying to get close to is going to be equal to 25. So somewhere along the y-axis that's going to be equal to 25, and this is a rough estimate of the plot. Apparently I'm not good at drawing diagrams. So basically that's another example of a quadratic function for a particular limit. Let's move on to a different example now. So this example will be focusing on a constant function, which is kind of different in a way. It's not as difficult as the previous example, but it's different to think about. So let's consider the function fx equals 4, right? So what would this function look like? Just think about it for a second. For all particular values of x, it's giving the same value 4. So in this case, my function turns out to be fx equals 4. This is the x-axis and that's the y-axis, right? So basically what I'm trying to prove over here is that limit for all particular values of x approaching a particular value a has to equal 4. So this basically means for all particular values of x, right? So what I'm saying is that regardless of the value of x approaching a, regardless of the value of a for the function fx, which is a constant function, the limit has to be exactly one value. So what an application of what I'm trying to suggest over here is that limit of x approaches 1 for the function 4 is what exactly? So as we can see, the approach that we used in the previous examples was that for any particular value of x, all we did was plug in that particular value of x, right? But in this case we can observe that there's no value of x to plug it into. But what we can observe is it's a constant function. So regardless of the value of x, it has to be, the limit has to be equal to 4. And this is true for all particular values of a, where a is the variable that you might change depending on the situation you talk about. So if we were to think about it diagrammatically, if x has a value 1 over here, then we can observe the limit has to be equal to 4. So regardless of what point I'm at, the limit has to be equal to 4. So all these points will be giving us the same limit. This concept will be especially important in the next video, and we'll be talking about functions such as the step function and other cases in which we can use different techniques to simplify how we calculate a limit. See you guys in the next video.